2 in the morning. The nightly batch job is rewriting yesterday's swipes. At the same moment, a streaming job appends the last few minutes of transactions to the same table. Neither knows the other exists. By morning, some rows are missing. Not corrupted, missing. Neither log shows an error. Both jobs report success, and nobody can work out which one did it. 2 job icons writing into the same folder labeled swipes, both with green check marks, while the folder shows a jumble of files and a red question mark, captioned, "Both succeeded, data is wrong." That's a normal Tuesday with directory-based tables, and it's the problem this video is about. The fix turns out to be one small thing in one small place that most people using Iceberg never think about: the catalog. Last video ended on the question it answers. Every write creates a new snapshot, and all of them exist at once, side by side in storage. So something has to decide which snapshot is the current table, the one you get when you simply ask for the swipes table. 4 complete metadata trees in a row labeled snapshot 1 to 4. Above them, a small box labeled catalog with one arrow pointing at snapshot 4, captioned, "Which one is current?" The catalog does one job. For each table, it stores a pointer to that table's current metadata file. That's all. It doesn't hold your data, it doesn't hold your schema that's inside the metadata file. It holds a name and the location of one file. Ask it for the swipes table, and it hands back a path. Follow the path, and you're at the top of last video's tree. Several things can play this role: a dedicated Iceberg REST catalog, now the common standard, cloud services like AWS Glue, a plain relational database over JDBC, and, worth noting given how much we criticized Hive last video, the Hive metastore itself. That's the part people get muddled. Iceberg did not replace the Hive metastore. It replaced the Hive table format, the idea that a table is a directory and its contents are whatever files sit in it. The metastore, as infrastructure mapping table names to locations, can perfectly well hold an Iceberg pointer. What it couldn't do was define a table's contents, because that meant listing directories and tracking every partition in a database that slowed as tables grew. Which catalog you pick matters more than its size suggests, because it's the one component every engine must agree on. The data and metadata are just files and object storage. Anything can read them. But 2 engines only see the same table if they ask the same catalog which snapshot is current. Point Spark at one catalog and your query engine at another, and you have 2 tables that happen to share files. This is also where the lock-in question really lives. The format is open, so the risk was never the data, it's whether the thing holding the pointers is something you can walk away from, which is a large part of why an open REST catalog specification became such a focus. Now, why does one pointer fix our 2 o'clock disaster? Because it turns every possible change to a table into the same tiny operation. Follow a write-through. A job writes new data files, new manifests, a new manifest list, and a new metadata file. None of it is visible yet. A query asking the catalog still gets the old pointer and reads the old snapshot, unaware. Only at the end does the job ask the catalog to move the pointer. Before that moment, old table. After it, new table. No in between and no window where a reader sees half a job's work. So back to the batch job and the streaming job. Both read the catalog and see the current metadata file is version 4. Both do their work independently. Both come back wanting the pointer moved to their own new version. The catalog doesn't blindly accept. The request is conditional, effectively, move this pointer to my version, but only if it still points at version 4. The batch job gets there first, the condition holds, the swap succeeds. The streamin' job arrives moments later with the same condition, but the pointer now reads version 5. The condition fails, the swap is rejected. Nothing is lost or corrupted. The streaming jobs files sit in storage, but no metadata references them, so as far as any reader is concerned, they don't exist. The job reads the new current state and retries its append on top. This is optimistic concurrency. Everyone assumes they'll succeed, does the work, and the conflict is caught at the last instant by a conditional swap only one writer can win. Two job icons holding new trees, both reaching for the catalog. One arrow succeeds with a check labeled condition held. The other bounces off labeled pointer moved, retry. The missing rows from 2 in the morning can't happen, not because Iceberg is more careful, but because there's now exactly one place where what the table is gets decided, and changing it is a single, indivisible step. That same structure fixes the fourth Hive problem. Schema changes. The danger was columns tracked by name and position, so a rename or reorder could line data up against the wrong column, silently. Iceberg assigns every column a permanent numeric ID when it's created. The name you write in a query is a label pointing at that ID, and data files record which IDs they hold. Rename a column and the ID never changes, only the label does. Every existing data file still refers to the same ID, so nothing is misread and nothing is rewritten. Add a column and it gets a new ID old files don't contain, so they read as having no value for it. Drop one and readers stop asking for that ID. The bytes stay in the old files, harmlessly ignored. Renaming a column on a 300 terabyte table rewrites 0 bytes and takes about as long as the pointer swap. A column labeled amount with a badge reading ID equals 4. An arrow shows it renamed TXN amount, while the badge still reads ID equals 4. Below, 3 data files all still pointing at ID equals 4. That's the difference between schema changes being routine and being something a team avoids for years because the last one caused an incident. One more thing moves into metadata and it saves query writers the most daily pain. Partitioning. With plain files, partitioning is a folder layout and it leaks. Our swipes table is partitioned by day, so a query must filter on that exact derived column, spelled as the folders are spelled. Filter on the raw transaction timestamp instead, and the engine can't match it to a folder, so it scans all 730 days to answer a question about one. Iceberg records the relationship instead. This table is partitioned by the day derived from the transaction timestamp. You filter on the timestamp the natural way, and Iceberg applies that relationship itself to work out which partitions to skip. That's hidden partitioning, genuinely hidden, because the table knows how to use it on your behalf. A query box reading where TS between with a clean arrow into a table icon. Beneath, a small gear labeled day of TS in a dashed box captioned, "The table applies this, not you." So, one pointer, held by a catalog, changed by a conditional swap, only one writer can win. That single mechanism gives atomic commits, safe concurrent writes, and somewhere to keep schema and partitioning as versioned facts, rather than conventions everyone must remember. A closing strip. Catalog equals one pointer per table, commit equals conditional swap, schema equals permanent column IDs, partitioning equals the table's job. Next time, you delete 10 million rows from this table and your storage bill goes up. That's not a bug, and understanding why explains almost everything else Iceberg can do.